Welcome to Deep Science Sleep. Let yourself settle in comfortably. Take a slow, deep breath. As you exhale, allow the concerns of the day to drift away like autumn leaves on a gentle stream. Tonight, we're embarking on a journey through the cosmos to witness one of nature's most patient and profound transformations. We're going to explore the silent birth of a star. This is a story that unfolds over millions of years in the deepest cold and darkness of space, where temperatures hover just a handful of degrees above absolute zero. It's a story of matter and energy, of gravity's slow and inexorable pull, of heat building in darkness, and ultimately, of light emerging from shadow. As you listen, let the vast timescales wash over you. Let the cosmic perspective ease your mind into a state of peaceful rest. There is no hurry here, no urgency. We have all the time in the universe. Close your eyes and imagine yourself drifting, weightless, through the velvet darkness between the stars. You're safe, warm, perfectly at peace, floating through a realm where human concerns fade to nothing against the backdrop of stellar creation. The cosmic cradle, understanding molecular clouds. Our story begins not with light, but with darkness. Not with heat, but with cold. Not with something, but with what appears at first to be nothing at all. Yet within this apparent emptiness lies the raw material for countless suns, for entire planetary systems, for worlds we cannot yet imagine. Scattered throughout our Milky Way galaxy are enormous clouds of gas and dust, drifting through the void like cosmic islands in an infinite ocean. These are molecular clouds, the stellar nurseries where stars are born. They are among the coldest places in the known universe, with temperatures ranging from a mere 10 to 30 degrees above absolute zero. At such frigid temperatures, even the fundamental nature of matter changes. Atoms slow their eternal dance, drawing together, combining into molecules. Hydrogen, the simplest and most abundant element in the cosmos, pairs with itself to form molecular hydrogen. This is the fundamental building block of star formation, the raw fuel from which suns are kindled. Carbon atoms join with oxygen to create carbon monoxide, which serves as a tracer gas, allowing astronomers to map these vast, dark clouds across the light years. Within these frigid depths, molecules of water ice, ammonia, even complex organic compounds drift and gather, settling onto tiny grains of dust no larger than particles of smoke. The scale of these molecular clouds defies easy comprehension. A typical giant molecular cloud might stretch across 100 light-years of space. To put this in perspective, light itself, traveling at its ultimate cosmic speed limit of 186,000 miles per second, would take a full century to cross from one side to the other. Within this volume, masses equivalent to anywhere from 10,000 to 10 million times that of our sun drift in the darkness, invisibly cold, patiently waiting. These clouds are not uniform. They are turbulent, chaotic, irregular in shape. They have no clearly defined boundaries, no smooth edges. Instead, they twist and curl like smoke from incense, forming convoluted serpentine shapes, dense filaments, and hollow cavities. The largest of these dark clouds are visible to the naked eye from Earth as patches of darkness set against the bright background of the Milky Way. The Coalsack Nebula in the southern sky appears as a conspicuous dark void, a window into true cosmic emptiness. Yet this emptiness is an illusion. Within these clouds, the density of matter is still incredibly low by earthly standards. In the most diffuse regions, you might find only 100 to 300 molecules per cubic centimeter. For comparison, the air you're breathing right now contains about 10 million trillion molecules in the same volume. Even in the densest cores of molecular clouds, where star formation is most active, densities might reach only 10,000 to 1,000,000 molecules per cubic centimeter. By human standards, these clouds represent a vacuum far more perfect than anything we can create in our laboratories. Yet, by the standards of interstellar space, they are remarkably dense, remarkably substantial. The Orion Molecular Cloud Complex, lying some 1,300 to 1,500 light-years from Earth, represents one of the most studied stellar nurseries within reasonable proximity to our solar system. When you look at the constellation of Orion on a winter's night, the middle star in the Hunter's Sword is not a star at all, but rather the Orion Nebula, a brilliant region where the molecular cloud is actively giving birth to new stars. Within this complex, over 3,000 young stellar objects have formed in just the last few million years. The cloud glows with the light of newborn stars, their radiation ionizing the surrounding hydrogen gas, causing it to emit the characteristic red glow of hydrogen alpha light. The Eagle Nebula, catalogued as Messier 16, lies farther away, some 5,700 light-years distant in the constellation Serpens. This cloud, immortalized in the Hubble Space Telescope's famous Pillars of Creation image, shows towering columns of cold molecular gas and dust, some of them stretching across 9.5 light-years. These pillars are being sculpted and eroded by the ultraviolet radiation from young, massive stars that have already formed from the cloud. At the tips of these pillars, at their densest points, new stars are still forming, emerging from structures called EGGs, or evaporating gaseous globules. The Taurus molecular cloud, closer to us at only about 430 light-years away, represents a gentler example of star formation. Here, the process unfolds more slowly, more quietly. Low-mass stars like our Sun are being born in relative isolation, without the violent radiation and stellar winds of massive stars to disrupt the process. This cloud has become one of the most intensively studied regions for understanding how solar-type stars form. These molecular clouds are not permanent features of our galaxy. They are transient on cosmic timescales, lasting only a few million to perhaps 10 million years before they either form stars or are dispersed by various forces. Spiral density waves in the galactic disk can compress diffuse interstellar gas, triggering the formation of new molecular clouds. Supernova explosions from dying massive stars can send shock waves rippling through space, compressing nearby gas and dust into new clouds. The collision of smaller clouds can create the conditions for a giant molecular cloud to assemble. Once formed, these clouds drift through the galaxy, dark and silent, undetectable at visible wavelengths. Only through radio and infrared observations can we peer into their hearts and study the processes unfolding within. The molecular hydrogen that comprises most of their mass is notoriously difficult to observe directly, as it emits very little radiation at these frigid temperatures. Instead, astronomers use carbon monoxide as a proxy, tracking its microwave emissions to map the distribution and motion of the clouds. Within these vast, cold expanses, chemistry happens. Despite the extreme cold and the incredibly low densities, molecules form on the surfaces of dust grains. water ice accumulates. Organic compounds, some of them surprisingly complex, assemble from simpler precursors. Amino acids, the building blocks of proteins, have been found in meteorites that represent pristine material from the early solar system. These compounds formed in a molecular cloud over 4.5 billion years ago, incorporated into solid bodies during planet formation, and eventually found their way to Earth. The chemistry of life itself may have its origins in these dark, cold stellar nurseries. The clouds are threaded by weak magnetic fields, typically only a few millionths as strong as Earth's magnetic field, but extending across light years. These magnetic fields provide some support against gravitational collapse, but they are not strong enough to prevent it indefinitely. Over time, through a process called ambipolar diffusion, neutral atoms drift slowly through the magnetic field, concentrating in the densest regions while the charged particles remain coupled to the field lines. This gradual separation of matter from magnetic support is one of the processes that can eventually trigger the formation of a new star. As you drift in your mind's eye through one of these molecular clouds, imagine the profound stillness, the absolute silence of this cosmic womb. No sound can travel through this near vacuum. No light penetrates the depths. The temperature is so low that all motion nearly ceases. And yet, despite this apparent stillness, this seeming emptiness, something extraordinary is about to happen. Within the densest regions of the cloud, in cores no more than a few light years across, gravity is beginning to gain the upper hand. The long, slow process of stellar birth is about to begin. The first stirrings, gravitational collapse begins. For eons, the molecular cloud has drifted in equilibrium, balanced between the inward pull of its own gravity and the outward push of its internal pressure. The gas pressure, even at these incredibly low temperatures, exerts a force that resists compression. The cloud maintains a kind of cosmic poise, neither collapsing nor expanding, simply existing in the darkness between the stars. But equilibrium is fragile. It takes only the slightest disturbance to tip the balance. Perhaps a nearby star, reaching the end of its life, explodes as a supernova. The shock wave from this cosmic detonation ripples outward at thousands of kilometers per second, slamming into the molecular cloud. The impact compresses the gas, increasing its density in localized regions. These compressed zones now have stronger gravitational fields, pulling more strongly on the surrounding material. The balance has been broken, or perhaps the trigger is more subtle. Our galaxy is a spiral galaxy, and within the plane of the disk, density waves rotate more slowly than the stars themselves. When the molecular cloud passes through one of these spiral arms, it encounters higher density material and experiences a gravitational squeeze. This compression might be all it takes to push certain regions past the critical threshold. Sometimes, two molecular clouds collide. Despite the vast emptiness of space, on timescales of millions of years, such encounters are inevitable. When clouds merge, the turbulent interface between them creates shocks and compressions. New dense cores form at the intersection. Whatever the trigger, once a region of the molecular cloud becomes dense enough, massive enough, gravity begins to dominate. There exists a critical mass called the Jeans mass after the British physicist James Jeans, who first calculated it, above which gravitational forces overcome thermal pressure. For the cold temperatures in molecular clouds, This critical mass is relatively small by stellar standards, perhaps only a few times the mass of our Sun. Once a clump exceeds this threshold, collapse becomes inevitable. The collapse does not happen all at once. It begins in the very center of the densest core, where the gravitational pull is strongest. Material at the center falls inward, pulled by its own weight. This increases the density at the center, which strengthens the gravitational field, which pulls even more material inward. The process becomes self-reinforcing, a slow avalanche of matter falling toward a central point. Theoretical models of this collapse, first developed in detail in the mid-20th century, predict that the collapse should spread from the inside outward, like a wave moving through the cloud. The center collapses first, while the outer layers continue to fall inward at subsonic speeds. This inside-out collapse has been confirmed by spectroscopic observations of dense cores that are just beginning their transformation into stars. As the core contracts, several fundamental physical principles come into play, shaping the evolution of the collapsing cloud. The first is the conservation of angular momentum. The cloud, vast as it is, has some small amount of rotation. It might be rotating so slowly that it would take millions of years to complete a single turn. But as the cloud collapses and shrinks in size, just as an ice skater spins faster when pulling in their arms, the collapsing cloud must spin faster to conserve angular momentum. This rotation has profound consequences. As the cloud spins faster, centrifugal force begins to oppose the inward collapse in the equatorial plane. Material falling toward the center from the poles encounters little resistance from rotation, but material falling inward at the equator finds itself pushed outward by centrifugal effects. The result is that the spherical cloud begins to flatten. It takes on the shape of a disk, with material continuing to fall inward along the rotation axis while the equatorial regions spread outward. The second key principle is the conservation of energy. As material falls inward under gravity, it loses gravitational potential energy. This energy doesn't disappear. It converts into kinetic energy, the energy of motion. The particles falling inward move faster and faster, but they don't fall forever in straight lines. They collide with other particles. These collisions convert the ordered motion of infall into random thermal motion. The temperature begins to rise. This is one of the most remarkable aspects of stellar birth. The cloud is collapsing, growing denser, yet simultaneously it is heating up. In the depths of the coldest regions of space, a pocket of warmth is beginning to form. The temperature at the center of the collapsing core climbs from 10 or 20 degrees above absolute zero to hundreds, then thousands of degrees. As the core collapses, it also fragments. The turbulent, chaotic internal structure of the original molecular cloud means that there are multiple dense clumps, multiple local concentrations of matter. Each of these can begin its own collapse, forming its own protostar. This is why stars typically form in clusters rather than in isolation. A single molecular cloud core with a mass of 10,000 times that of the Sun or more might fragment into hundreds or thousands of individual star-forming clumps. The fragmentation occurs at multiple scales. The large-scale molecular cloud breaks into smaller cores, each a fraction of a light-year across. These cores, in turn, break into even smaller clumps, only a tenth of a parsec in size, with masses ranging from 10 to perhaps 50 times that of our Sun. These clumps continue to collapse, And it is from these fragments that individual stars or small multiple star systems will eventually form. Observations of star-forming regions reveal this hierarchical structure. In the Orion Nebula, for instance, we see not just individual protostars but groups of them clustered together. The trapezium cluster at the heart of the Orion Nebula contains some of the youngest, hottest, most massive stars in the region, all formed from the same parent cloud within the last few million years. Surrounding them are hundreds of fainter, cooler, lower-mass stars in various stages of formation. The entire process of fragmentation and initial collapse takes roughly 10 million years. This is, by cosmic standards, a relatively brief period. It's shorter than the time that has elapsed since our human ancestors diverged from other great apes. Yet by human standards, it is an eternity, a span of time almost impossible to grasp intuitively. Imagine a process so slow that if you could somehow observe it continuously, you would see no perceptible change over the course of your entire lifetime, nor over the lifetimes of 1,000 generations. Only on timescales of millions of years does the transformation become apparent. Throughout this long collapse, the dense core becomes increasingly opaque. The dust grains suspended within the gas begin to absorb any radiation trying to escape from the interior. Light that might have been emitted by the warm gas at the center cannot penetrate the surrounding layers of cold, dense material. The collapsing core becomes a dark nebula, a silhouette against the background stars, or against the glow of nearby regions where star formation has already proceeded further. At the very center of the collapse, where the density is now millions of times higher than in the original cloud, where the temperature has climbed to thousands of degrees, a new object is taking shape. It is not yet a star. It does not shine by nuclear fusion. It is still gathering mass from its surroundings, still growing, still being built by the slow rain of matter from the collapsing envelope. But it has crossed a threshold. It has become dense enough, warm enough, distinct enough from its parent cloud to warrant a new name. It is now a protostar. The transition from collapsing cloud core to protostar is gradual, not sudden. There is no single moment when we can point and say, "There, now it is a protostar." Rather, it is a continuum, a slow evolution from diffuse cloud to distinct central object. But by the time the central temperature has reached a few thousand degrees and the central density has climbed to billions of molecules per cubic centimeter, the transformation is effectively complete. A protostar has been born from darkness and cold, warmed by its own gravitational contraction, yet still invisible to optical telescopes, still hidden within its cocoon of dust and gas. Birth of the protostar, heat without light. At the heart of the collapsing cloud core, surrounded by layers of infalling matter, the protostar begins its existence in profound obscurity. It is warm, even hot by the standards of the frigid cloud from which it formed, but it does not yet shine with its own light in any wavelength we could see with our eyes. Its energy comes not from nuclear reactions in its core, but from the simple conversion of gravitational potential energy into heat as matter continues to fall onto its surface. The protostar at this stage is much larger than it will eventually become. A young protostar destined to become a star like our Sun might have a radius several times larger than the Sun's current size, extending perhaps 10 or 20 times farther from its center than the final star will. This bloated structure is not in stable equilibrium. It is still contracting, still compressing under its own weight, though now more slowly than during the initial collapse phase. The surface temperature of the protostar is relatively cool, perhaps only a few thousand degrees. For comparison, the surface of our Sun is about 5,700 degrees Kelvin. The protostar is cool enough that molecules can still exist in its outer layers, and its radiation peaks in the infrared part of the spectrum, invisible to human eyes but detectable with infrared telescopes. To infrared eyes, the protostar appears as a source of warmth in the cosmic cold, a beacon of thermal emission surrounded by cooler dust. Material continues to rain down onto the protostar from the surrounding envelope. This infalling material does not land gently on the surface. It crashes down at high velocity, having been accelerated by gravity during its long fall from the outer reaches of the cloud core. When this material hits the protostar's surface, the kinetic energy of its motion converts suddenly into heat, creating shock waves in the protostar's outer layers. These shocks heat the gas to tens of thousands of degrees locally, though this heat radiates away relatively quickly. The rate at which material falls onto the protostar determines how quickly it grows. Early in the protostar's life, the accretion rate might be relatively high, perhaps 1/10,000th of a solar mass per year. This might not sound like much, but at this rate, the protostar can double its mass in just 100,000 years. As the surrounding envelope gradually depletes, the accretion rate declines, and the protostar's growth slows. Not all of the collapsing cloud's mass ends up in the protostar. As noted earlier, the conservation of angular momentum causes the infalling material to form a disk rather than falling directly onto the protostar. This disk, orbiting in the equatorial plane of the system, is initially quite large, extending outward for hundreds or even thousands of times the distance from Earth to the Sun. The disk is the progenitor of a planetary system, though planet formation is still far in the future. The disk itself is not uniform. It has temperature gradients, with the inner regions closer to the warm protostar being hotter than the outer regions. Near the protostar, temperatures might be high enough to vaporize rock and metal, while in the outer disk, water and other volatile compounds can condense into ice. This temperature structure will eventually determine which types of planets form where, with rocky planets forming in the hot inner regions and gas and ice giants forming farther out. The disk is also not static. Material within the disk gradually spirals inward toward the protostar, driven by a process that is still not completely understood despite decades of research. The material in the disk is in orbit, and for it to spiral inward, it must somehow lose angular momentum. This requires some form of viscosity or turbulence within the disk to transport angular momentum outward while allowing mass to move inward. Magnetic fields threading through the disk may play a crucial role in this process, creating turbulence through an instability called the magnetorotational instability. As material from the disk spirals onto the protostar, it releases additional gravitational energy, further heating the system. The inner edge of the disk, where it meets the protostar, is a region of intense activity. Material here is moving at high speeds, heated to thousands of degrees, emitting strongly in the ultraviolet and X-ray regions of the spectrum. This radiation, though invisible to our eyes, floods the surrounding disk and envelope, driving complex photochemistry and influencing the structure of the disk. Deep within the protostar's interior, the core continues to contract and heat. The temperature at the center might now be approaching 100,000 degrees or more. At these temperatures, atoms are fully ionized, stripped of their electrons, existing as a plasma of bare nuclei and free electrons. The density has reached values far higher than any solid material on Earth, with hundreds of grams of matter compressed into every cubic centimeter. Despite these extreme conditions, the protostar's core is still too cold for nuclear fusion of ordinary hydrogen. Fusion requires temperatures of at least 10 million degrees, and the protostar has not yet reached that threshold. However, something interesting does begin to happen at temperatures around 1 million degrees. The protostar contains trace amounts of deuterium, a heavy isotope of hydrogen whose nucleus contains both a proton and a neutron rather than just a proton. Deuterium is far easier to fuse than ordinary hydrogen. At temperatures of only 1 million degrees or so, deuterium nuclei can collide with enough energy to overcome their electrical repulsion and fuse together, or fuse with ordinary hydrogen nuclei to form helium-3. This deuterium fusion releases energy, though far less than will eventually be produced by hydrogen fusion. The energy from deuterium burning helps to slow the protostar's contraction temporarily, acting like a thermostat that regulates the internal temperature. All stars pass through this deuterium burning phase during their early evolution. The amount of deuterium available is quite small, typically only about 1 deuterium atom for every 50,000 hydrogen atoms. This fuel is quickly exhausted, burned through in perhaps 100,000 years. Once the deuterium is gone, the protostar resumes its contraction, its core temperature rising once more. The protostar will spend most of its early life, several million years, in this state, accreting matter from the surrounding disk and envelope, slowly contracting, slowly heating, burning what deuterium it has but not yet hot enough for sustained hydrogen fusion. During this time, it exists in a delicate balance. The energy generated by gravitational contraction and the accretion of matter must somehow escape from the interior, radiating away into space. If this energy could not escape, the protostar would heat up rapidly and halt its contraction. The transport of energy from the protostar's core to its surface occurs through two main mechanisms: radiation and convection. In the deep interior, where temperatures are highest, photons of light carry energy outward. However, these photons don't travel far before being absorbed and re-emitted by the dense plasma. A single photon might take hundreds of thousands of years to random walk its way from the core to the surface. In the outer layers of the protostar, where temperatures are lower, convection becomes important. Hot plasma rises from deeper layers, cools as it approaches the surface, and then sinks back down to be reheated. This convective motion is similar to the churning motion in a pot of boiling water, though occurring on a vastly larger scale and driven by the intense heat from below rather than a stove burner. The protostar's surface temperature remains relatively cool throughout this phase, generally less than 4,000 degrees. This gives the protostar a reddish color, though it remains far too deeply embedded in its dusty envelope to be observed directly at optical wavelengths. The infrared radiation from the protostar and its immediate surroundings heats the surrounding dust, causing it to glow in the far infrared. This is how astronomers can detect protostars even when they cannot see them directly. The protostar's mass determines its future evolution. A more massive protostar contracts faster, heats up more quickly, and will spend less total time in the protostellar phase before igniting hydrogen fusion. A less massive protostar evolves more slowly, taking longer to heat its core to the fusion threshold. For a protostar with about 1 solar mass, destined to become a star like our Sun, the protostellar phase lasts approximately 500,000 to 1 million years. There is a lower mass limit for star formation. If the collapsing cloud core has a mass less than about 0.08 of a solar mass, roughly 80 times the mass of Jupiter, the resulting protostar will never become hot enough to sustain hydrogen fusion. These failed stars, called brown dwarfs, are doomed to shine only by the heat of their initial gravitational contraction, cooling slowly over billions of years. They occupy a twilight zone between planets and stars, neither one nor the other, massive enough to have formed like stars but not massive enough to become true stars. There is also an upper mass limit, though it is less sharply defined. Protostars with masses exceeding perhaps 150 to 200 times that of the Sun become so luminous during their formation that the radiation pressure from their intense light can halt or even reverse the infall of matter. These most massive stars probably form through different processes, perhaps through the merger of smaller protostars or through unusually rapid accretion in the densest regions of molecular clouds. As the protostar continues its slow evolution, imperceptibly changing from day to day, from year to year, but transforming dramatically over millennia and eons, it remains embedded in its natal environment. The disk surrounding it grows in mass as material from the outer envelope continues to fall onto it. The protostar itself accretes matter from the inner disk. And throughout the system, complex interactions between gravity, rotation, magnetic fields, and radiation shape the structure and evolution of this cosmic nursery. The accretion dance, building a star. The disk surrounding the protostar is not merely a passive reservoir of material. It is a dynamic structure, a swirling maelstrom of gas and dust engaged in an intricate gravitational dance. Understanding this disk and how material moves through it is crucial to understanding how the protostar grows and how the seeds of planets are sown. In the disk's outer regions, tens or hundreds of astronomical units from the protostar, temperatures are low, only a few tens of degrees above absolute zero. Here, water ice, methane ice, and ammonia ice can condense onto dust grains, coating them in frosty layers. The gas is thin, the pressure low, and the orbital motion slow. A parcel of gas at the outer edge of the disk might take hundreds or thousands of years to complete a single orbit. Moving inward, temperatures rise. The inner disk, within a few astronomical units of the protostar, can reach temperatures of hundreds or even thousands of degrees. Here, any ice that might have condensed has evaporated back into gas. Only refractory materials, silicates and metals that can withstand high temperatures remain as solid particles. The gas is denser here, the pressure higher, and the orbital velocities much faster. Material in the inner disk whips around the protostar in a matter of years or even months. The disk is threaded by magnetic fields. These fields, though weak compared to laboratory magnets, extend across vast distances and interact with the ionized gas in the disk. Where the gas is fully ionized, it is tightly coupled to the magnetic field, and the field can exert significant control over the motion of the gas. In the cooler, more neutral regions of the disk, the coupling is weaker, and the gas can drift through the field. The interaction between the rotating disk and the magnetic fields of the protostar creates one of the most striking features of young stellar systems: bipolar outflows and jets. At the interface between the protostar and the inner edge of the disk, the protostar's magnetic field lines extend outward, connecting to the disk. Material from the disk can fall onto the protostar along these field lines, funneling down toward the magnetic poles. As this material accelerates along the field lines, it can reach velocities of hundreds of kilometers per second. When it crashes onto the protostar's surface near the poles, it creates hot spots that can emit strongly in X-rays and ultraviolet light. But some of the material never makes it to the surface. Instead, it is accelerated outward along the magnetic field lines, ejected in narrow, collimated jets that shoot out from the protostar's poles. These jets are among the most dramatic and photogenic features of star formation. They can extend for light years, plowing through the surrounding molecular cloud at supersonic speeds. Where the fast-moving jet material slams into the slower-moving ambient gas, it creates shock waves that heat the gas to thousands of degrees, causing it to glow. These glowing knots and patches of nebulosity are called Herbig-Haro objects, named after the astronomers George Herbig and Guillermo Haro, who first studied them systematically. The jets serve a critical function in the star formation process. They carry away angular momentum from the system. Remember that the collapsing cloud had some net rotation, and this angular momentum cannot simply disappear. It must go somewhere. If all the mass in the disk tried to fall onto the protostar while retaining its angular momentum, the protostar would spin so fast it would tear itself apart. The jets, by ejecting material at high velocities along the rotation axis, carry away angular momentum without removing much mass. This allows the bulk of the disk material to continue spiraling inward onto the protostar. In addition to the narrow, fast jets, many young protostars also drive wider, slower outflows. These are partially ionized winds that emerge from the surface of the disk rather than from the protostar itself. The disk wind is driven by heating from the protostar's ultraviolet and X-ray radiation, which heats the surface layers of the disk to high temperatures. Where this thermal energy overcomes the gravitational binding energy, gas escapes from the disk and flows outward. Observations of young stellar systems reveal a variety of outflow phenomena. Some protostars have episodic jets, with knots of material ejected at intervals that might be separated by decades or centuries, perhaps related to variations in the accretion rate onto the protostar. Others show continuous flows. Some have jets that appear straight and narrow, while others have jets that wiggle or precess, tracing out helical patterns in space. All of this activity, the jets and outflows, represents only a small fraction of the mass in the system, perhaps 1% or less. The vast majority of the disk mass, 99% or more, continues its slow spiral inward toward the protostar. The process by which this material moves through the disk is complex and has been the subject of intense research. At a basic level, the inward motion of disk material is driven by viscosity, a kind of friction within the gas. Material in the inner disk, closer to the protostar, orbits faster than material in the outer disk, following Kepler's laws of orbital motion. This differential rotation creates shear within the disk. Viscosity acts to smooth out this shear, transferring angular momentum outward and allowing mass to drift inward. However, the amount of viscosity in a thin disk of gas should be very small, far too small to account for the observed accretion rates. Something must be enhancing the effective viscosity. For many years, astronomers suspected that turbulence within the disk was responsible, but the source of this turbulence remained mysterious. In the early 1990s, A breakthrough came with the discovery of the magnetorotational instability. The magnetorotational instability operates in any rotating disk that is threaded by magnetic fields and that has even weak viscosity. Small perturbations in the disk can become unstable, growing rapidly and creating turbulence. This turbulence effectively increases the viscosity by many orders of magnitude, allowing mass to flow inward at rates consistent with observations. The discovery of this instability revolutionized our understanding of accretion disks, not just around protostars but also around white dwarfs, neutron stars, and black holes. As mass accretes onto the protostar, it releases gravitational potential energy. This energy heats the inner disk and the protostar itself. In fact, during the early stages of protostellar evolution, the energy released by accretion can exceed the energy generated by gravitational contraction of the protostar itself. The protostar is being powered, in a sense, by the rain of matter falling onto it from above. The accretion rate varies with time. Early in the protostar's life, when the envelope of gas around it is massive and dense, the accretion rate can be quite high. As the envelope depletes and the disk spreads out, the accretion rate declines. There can also be episodic variations. If a clump of material in the disk suddenly becomes unstable and spirals inward rapidly, the protostar might experience a dramatic outburst, briefly increasing in brightness by orders of magnitude before fading back to its quiescent level. These outbursts have been observed in some young stellar objects. They are called Fu Orionis outbursts after the star Fu Orionis, which experienced such an event in 1936. During an Fu Orionis outburst, the accretion rate can increase by a factor of 10,000 or more, and the luminosity of the system increases dramatically. The outburst can last for decades or even centuries before subsiding. These events may be a normal part of protostellar evolution, with most stars experiencing several such outbursts during their youth. The disk is not just a channel for delivering matter to the protostar. It is also the birthplace of planets. Within the disk, dust grains settle toward the midplane, forming a thin layer of solid particles embedded in the gas. These grains collide with each other at low velocities. Sometimes they stick together very slowly, growing into larger aggregates. This process of grain growth is poorly understood in detail, as there are many barriers to overcome. Grains that grow too large can bounce off each other rather than sticking. They can also drift inward through the gas disk faster than they can grow, eventually falling into the protostar before they can become large enough to be gravitationally bound. Yet somehow, in disks around real stars, grains do grow. We know this because we can see the evidence in the disks themselves, observed at millimeter wavelengths, and because planetary systems like our own exist. Over time, perhaps over 1 million years or so, some grains grow to kilometer-sized bodies called planetesimals. Once objects reach this size, their own gravity begins to play a role, allowing them to attract nearby material more effectively. Planetesimals can then grow into planetary embryos, moon-sized to Mars-sized bodies. These embryos, orbiting within the gas disk, can undergo violent collisions and mergers, eventually forming terrestrial planets in the inner disk and the cores of giant planets in the outer disk. Giant planet formation requires capturing a massive envelope of hydrogen and helium gas from the disk. This must happen quickly, before the disk dissipates. Observations suggest that protoplanetary disks typically survive for only a few million years, with most of the gas dispersing within 10 million years of the protostar's birth. This sets a strict time limit on giant planet formation. If the cores of giant planets don't form quickly enough to capture their gas envelopes before the disk dissipates, they will remain ice giants like Uranus and Neptune rather than becoming gas giants like Jupiter and Saturn. Throughout this period, the protostar continues to contract and heat. Its core temperature climbs toward the critical threshold needed for hydrogen fusion. The disk gradually loses mass, both through accretion onto the protostar and through photoevaporation driven by ultraviolet radiation. The outflows and jets continue to shape the surrounding environment, carving out cavities in the molecular cloud and illuminating Herbig-Haro objects along their paths. By the time the protostar has been growing for a few million years, it has accreted most of the mass it will ever have. The disk around it has thinned considerably. The rate of accretion has dropped to a trickle. The protostar is approaching the end of its embedded phase, when it will finally emerge from its cocoon of gas and dust to reveal itself to the universe. Stellar winds and jets. The violent beauty. The young stellar system is a realm of paradox. On one hand, it represents creation, the birth of new worlds, the gentle accumulation of matter under gravity's patient pull. On the other hand, it is a region of extreme violence, with supersonic winds, powerful jets, intense radiation, and titanic outflows that reshape the cosmic landscape around the forming star. As the protostar continues to accrete matter and grow, it transitions through different stages of evolution, each characterized by different observational properties and different physical processes. Astronomers classify young stellar objects into several categories based on the shape of their spectral energy distribution, the pattern of light they emit across different wavelengths. Class 0 objects are the youngest, still deeply embedded in their natal envelopes. Most of their mass is still in the surrounding envelope rather than in the central protostar. They are detectable only at far-infrared and millimeter wavelengths. Class 1 objects have accreted more of their final mass, with the envelope becoming less dominant. They emit more strongly at near-infrared wavelengths. Class 2 objects, also known as T-Tauri stars in the case of low-mass stars, have largely dispersed their envelopes and are now visible at optical wavelengths, though they still retain substantial circumstellar disks. Class 3 objects have lost most of their disk material and are approaching the main sequence. T-Tauri stars, named after the prototype star T-Tauri in the constellation Taurus, are particularly interesting objects. These are young stars, typically less than 10 million years old, with masses less than about 3 times that of the Sun. They have reached the stage where they are visible at optical wavelengths, no longer completely obscured by dust. They are still contracting toward the main sequence, not yet undergoing stable hydrogen fusion in their cores, but they have progressed far beyond the deeply embedded protostar stage. T-Tauri stars are characterized by several distinctive features. They show irregular variations in brightness, sometimes changing by a magnitude or more over periods of days to months. These variations are caused by a combination of factors: changes in the accretion rate, rotation of hot spots on the stellar surface, and the passage of dusty clumps in the inner disk across our line of sight. They have strong emission lines in their spectra, particularly hydrogen lines like hydrogen alpha. These emission lines indicate that there are regions of hot, ionized gas surrounding the star. Some of this emission comes from the accretion shocks where material from the disk impacts the stellar surface. Some comes from stellar winds being driven off the star's surface. Some comes from the base of jets. Many T Tauri stars show evidence for powerful winds. These winds are much stronger than the solar wind that flows from our sun today. T Tauri winds can carry away a significant fraction of a solar mass over the course of 1 million years. The wind is driven by a combination of thermal pressure, where the hot gas at the stellar surface expands outward, and magnetic pressure, where the star's magnetic field helps to accelerate charged particles to high velocities. The magnetic fields of T Tauri stars are remarkably strong, often thousands of times stronger than the sun's current magnetic field. These strong fields are generated by a dynamo mechanism in the star's convective interior. The rapid rotation of the young star, combined with convective motions, generates powerful magnetic fields that extend outward from the star and thread through the inner disk. Where the stellar magnetic field lines connect to the disk, they can funnel material from the disk onto the star along the field lines. This magnetospheric accretion occurs at the interface between the inner edge of the disk and the star itself. The inner edge of the disk is truncated at the radius where the stellar magnetic field becomes strong enough to disrupt the disk. Inside this radius, the gas falls onto the star along the magnetic field lines rather than orbiting in the disk. The infalling gas follows the field lines down to the stellar surface, channeled toward the magnetic poles. As it approaches the star, it accelerates to hundreds of kilometers per second. When this high-velocity stream of gas crashes into the stellar photosphere, it creates a strong shock. The shock heats the gas to temperatures of millions of degrees, causing it to emit X-rays and extreme ultraviolet radiation. These accretion hotspots can be detected on the surfaces of T Tauri stars, rotating in and out of view as the star spins. Not all the material that reaches the magnetosphere falls onto the star. Some of it is deflected and accelerated outward along field lines that open into interstellar space. This material forms the jets that are so prominent in images of star-forming regions. The jets are highly collimated, meaning they are very narrow compared to their length. A jet might be only a few astronomical units wide but extend for several light years. The jets travel at velocities of 200 to 400 kilometers per second, fast enough that when they slam into the surrounding molecular cloud, they create powerful shocks. These shocks heat the gas, causing it to emit light at specific wavelengths corresponding to forbidden emission lines of elements like oxygen, sulfur, and nitrogen. It's these emission lines that make Herbig-Haro objects visible. Herbig-Haro objects appear as bright knots and filaments of nebulosity, often arranged in chains along the axis of the jet. The knots represent locations where the jet has plowed into a particularly dense clump of material, or where episodic variations in the jet's velocity have caused faster-moving material to overtake slower-moving material, creating internal shocks. The filaments mark the edges of the jet's interaction with the ambient medium. Some of the most famous Herbig-Haro objects have been studied in exquisite detail with the Hubble Space Telescope. HH-111, for instance, shows a spectacular jet extending for over 2 light-years, with numerous knots and bow shocks visible along its length. The source of the jet is a deeply embedded protostar that is invisible at optical wavelengths but detectable in the infrared. HH-30 shows edge-on view of a disk around a young star, with a jet emerging perpendicular to the disk plane, beautifully illustrating the connection between disk accretion and jet formation. The jets carry away not just matter but also energy and angular momentum. A typical jet might carry away mass at a rate that is 10% or less of the accretion rate onto the star. But because the jet material is moving at such high velocities, it carries away significantly more energy and angular momentum per unit mass than the accreting material delivers. This extraction of angular momentum is crucial for allowing the star to continue accreting without spinning itself apart. The exact mechanism by which jets are launched and collimated is still a topic of active research. The leading models involve magneto-hydrodynamic processes, where the rotation of the disk combined with the magnetic field creates a magnetic centrifugal force that accelerates material outward along the field lines. The field lines themselves may be twisted by the differential rotation of the disk, creating a helical structure that helps to collimate the flow. Observations support these models. Jets often show evidence of rotation, with material on one side of the jet moving toward us and material on the other side moving away, consistent with a rotating outflow. The jets also show variability, with knots appearing at intervals that might be related to variations in the accretion process or to changes in the magnetic field configuration. In addition to the narrow jets, many young stars also drive wider, slower molecular outflows. These outflows consist of molecular gas, primarily carbon monoxide, moving at velocities of tens of kilometers per second. They can extend for parsecs, encompassing regions far larger than the jets themselves. The molecular outflows are thought to be driven by the interaction between the jet and the surrounding molecular cloud. As the jet plows through the cloud, it sweeps up ambient material, entraining it and accelerating it outward. The result is a broader, slower flow that still carries significant energy and momentum. These outflows have a profound impact on the molecular cloud from which the star is forming. They inject turbulent energy into the cloud, potentially providing support against further gravitational collapse in some regions, while triggering new collapse in other regions through the compression of gas. They also help to disperse the cloud, limiting the efficiency of star formation. Only about 10 to 30% of a molecular cloud's mass typically ends up in stars. The rest is dispersed or remains as diffuse gas. The T-Tauri phase lasts for several million years. During this time, the star continues to contract slowly, its core temperature steadily rising. The accretion rate gradually declines as the disk loses mass. The disk itself evolves, with the inner regions clearing out as material either accretes onto the star or is dispersed by photoevaporation. Dust grains in the disk continue to grow and settle, forming larger bodies that may eventually become planets. Eventually, the disk begins to develop gaps and holes. These gaps may be carved by newly formed planets sweeping up material in their orbits, or they may result from dynamical instabilities in the disk. Observations with the Atacama Large Millimeter Array and other advanced telescopes have revealed beautiful ring and gap structures in many protoplanetary disks, hinting at the complex processes of planet formation occurring within. As the disk mass declines and the inner disk clears, the star transitions from a classical T-Tauri star, which shows strong evidence of ongoing accretion, to a weak-line T-Tauri star, where accretion has largely ceased. The star is now primarily powered by its own gravitational contraction rather than by the energy released from accreting matter. It continues its slow approach toward the main sequence, where it will finally ignite hydrogen fusion and settle into a stable, long-lasting phase of stellar evolution. The critical threshold approaching fusion. Deep within the contracting protostar, in the very center where the pressure is highest and the temperature greatest, a transformation is approaching. The core has been steadily heating for millions of years, warmed by the relentless compression of gravity. The temperature has climbed from thousands to hundreds of thousands to millions of degrees. The density has increased to values that dwarf anything we experience on Earth, with hundreds of tons of matter compressed into every cubic meter. At these extreme temperatures and densities, matter exists in a state called plasma. The atoms that made up the original molecular cloud have been completely ionized, their electrons stripped away by violent collisions. What remains is a seething soup of bare atomic nuclei, mostly hydrogen nuclei which are simply protons, and free electrons buzzing about at tremendous velocities. The nuclei and electrons are in constant, frenetic motion, colliding, ricocheting, their speeds determined by the temperature of the plasma. Temperature in a plasma is just another way of expressing the average kinetic energy of the particles. The higher the temperature, the faster the particles are moving. At the core of the protostar, where temperatures have now reached several million degrees, protons are zipping about at speeds of hundreds of kilometers per second. They crash into each other millions of times per second, bouncing off in all directions. For nuclear fusion to occur, two protons must collide with enough energy to overcome the electrical repulsion between them. Both protons carry positive electrical charge, and like charges repel. This electrical repulsion, called the Coulomb barrier, is formidable. The closer two protons get to each other, the stronger the repulsive force becomes, pushing them apart. Only if they can get extremely close, to within about 1 femtometer or so, can the strong nuclear force take over, binding them together and allowing fusion to occur. At temperatures of 1,000,000 degrees, protons do collide with quite high energies. However, these energies are still typically too low to overcome the Coulomb barrier through classical physics alone. If fusion required protons to have enough energy to climb over the barrier in a purely classical sense, it wouldn't occur until temperatures reached hundreds of millions of degrees. Yet we know that hydrogen fusion begins at around 10 million degrees. How is this possible? The answer lies in quantum mechanics. In quantum theory, particles don't have precisely defined positions and velocities. Instead, they are described by probability distributions. A proton approaching another proton has some probability, even if small, of quantum mechanically tunneling through the Coulomb barrier rather than having to climb over it. This quantum tunneling effect dramatically lowers the temperature required for fusion. At 10 million degrees Kelvin, the temperature typically required for sustained hydrogen fusion to begin, most proton collisions still don't result in fusion. The tunneling probability is quite low for any individual collision. However, the number of collisions occurring every second in the star's core is staggeringly large. In every cubic centimeter, there are trillions of protons, and each one collides with others billions of times per second. Even though any particular collision has only a tiny chance of resulting in fusion, the sheer number of collisions ensures that fusion reactions occur at a significant rate. As the protostar's core temperature approaches 9, then 9.5, then 9.9 million degrees, the fusion rate remains negligible. A few fusion reactions might occur, but they contribute essentially no energy to the star. The star continues to shine solely by gravitational contraction, converting gravitational potential energy into thermal energy and radiation. But there is a critical threshold. Once the core temperature reaches about 10 million degrees, the fusion rate increases dramatically. The exponential dependence of the tunneling probability on temperature means that small increases in temperature above 10 million degrees lead to large increases in the fusion rate. Suddenly, the energy generated by fusion becomes significant. It begins to rival and then exceed the energy generated by gravitational contraction. The specific fusion process that powers stars like our Sun is called the proton-proton chain. It's a multi-step process, but it begins when two protons collide and, through quantum tunneling, fuse to form a nucleus of deuterium, a heavy isotope of hydrogen. This reaction also emits a positron and a neutrino. The positron quickly annihilates with an electron, converting its mass into energy according to Einstein's famous equation. The neutrino escapes from the star, carrying away a fraction of the energy. The deuterium nucleus then quickly fuses with another proton to form helium-3, releasing a gamma-ray photon in the process. Finally, two helium-3 nuclei can collide and fuse to form helium-4, releasing two protons back into the plasma. The net result of this chain of reactions is that 4 protons are converted into one helium-4 nucleus, 2 positrons, 2 neutrinos, and several gamma-ray photons. The mass of the helium-4 nucleus is slightly less than the combined mass of the 4 protons. This missing mass has been converted into energy, again according to Einstein's equation. The amount of energy released is enormous by everyday standards. Fusing just 1 kilogram of hydrogen into helium releases as much energy as burning several million kilograms of coal. As fusion begins to contribute significantly to the star's energy budget, it has a stabilizing effect on the star's structure. If the core temperature starts to rise above the equilibrium value, the fusion rate increases sharply. This increased energy generation heats the core further, but also increases the pressure, causing the core to expand slightly. This expansion cools the core, bringing the temperature back down. Conversely, if the core cools slightly, the fusion rate drops, pressure decreases, the core contracts, and the temperature rises again. This negative feedback mechanism, where increases in temperature lead to expansion and cooling, and vice versa, provides a thermostat that regulates the star's core temperature. It's the key to the long-term stability of main sequence stars. Once fusion begins in earnest and this thermostat kicks in, the star stops contracting. It reaches a state called hydrostatic equilibrium, where the outward pressure from the hot plasma exactly balances the inward pull of gravity at every point within the star. The protostar, now on the verge of this transition, has been contracting for millions of years. Its core temperature has been climbing inexorably toward the fusion threshold. The exact time it takes to reach this point depends on the star's mass. A star with twice the mass of the Sun will reach the main sequence in only a few tens of millions of years. A star with half the Sun's mass might take a few 100 million years. Our Sun, with its one solar mass, took approximately 50 million years to progress from the initial collapse of its parent molecular cloud to the ignition of stable hydrogen fusion. During this final approach to the main sequence, the protostar is classified as a pre-main sequence star. It is visible at optical wavelengths, having largely dispersed or outshone its dusty envelope. It is still contracting, still deriving some of its luminosity from gravitational energy, but it is rapidly approaching the end of this phase. On a diagram called the Hertzsprung-Russell diagram, which plots stellar luminosity versus surface temperature, pre-main sequence stars occupy a region distinctly different from the main sequence. They lie above and to the right of the main sequence, meaning they are cooler and more luminous than main sequence stars of the same mass. As they contract, they move across this diagram, tracing out evolutionary tracks that eventually converge on the main sequence. The final stages of contraction happen relatively quickly. As the core temperature approaches and then exceeds the critical threshold, the energy output from fusion ramps up rapidly. The star's contraction slows and then halts. The outer layers of the star adjust to the new internal structure, with the radius shrinking somewhat and the surface temperature increasing. The star settles onto the main sequence, ready to begin the longest phase of its life. Ignition. A star is born. There is no single instant when we can point and say, "There, now it is a star." The transition from protostar to main sequence star is gradual, occurring over thousands or tens of thousands of years. But there comes a time when hydrogen fusion in the core is generating enough energy to fully support the star against gravitational collapse. When the contraction has ceased, when the star has reached a stable configuration that it will maintain for billions of years. This moment, this transition, represents the true birth of a star. The object that began as a cold, dark clump of molecular gas has transformed into a blazing sphere of plasma, shining by the light of nuclear fusion. The star has crossed a threshold that only a tiny fraction of matter in the universe ever crosses. It has become a furnace, a nuclear reactor, a beacon of light and energy. The energy generated in the star's core by fusion must somehow make its way to the surface and escape into space. This journey is neither quick nor straightforward. A photon produced by a fusion reaction in the core of the Sun, for instance, will take thousands to hundreds of thousands of years to reach the surface. It doesn't travel in a straight line. Instead, it zigzags, being absorbed and re-emitted countless times, random walking outward through the dense plasma. In the core, the photons are gamma rays, extremely high-energy light. As they scatter through the star's interior, they gradually lose energy, their wavelength increasing. By the time radiation reaches the outer layers of the star, it has been degraded into a mix of X-rays, ultraviolet light, and visible light. At the star's surface, this light finally escapes into space, carrying away the energy generated deep in the core. The rate at which energy flows outward, and thus the star's luminosity, is determined by the rate of fusion reactions in the core. A more massive star has a hotter core, a faster fusion rate, and a higher luminosity. The relationship is steep. A star twice as massive as the Sun is about 10 times as luminous. A star 10 times as massive might be 1,000 times as luminous. This means that more massive stars burn through their fuel much faster. While our Sun will shine for about 10 billion years on the main sequence, fusing hydrogen in its core, a star 10 times as massive will exhaust its core hydrogen in only about 20 million years. The most massive stars, dozens of times the Sun's mass, might last only a few million years before running out of fuel. For a Sun-like star, the main sequence lifetime is comfortably long, measured in billions of years. During this time, the star undergoes only very gradual changes. The fusion of hydrogen into helium slowly enriches the core in helium, slightly increasing the core's density and temperature. This causes the fusion rate to increase very slowly over time, which in turn causes the star's luminosity to increase. Our Sun, for instance, is about 30% more luminous today than it was when it first reached the main sequence 4.5 billion years ago. But these changes occur on timescales of hundreds of millions to billions of years. On human timescales, on timescales of thousands or even millions of years, a main sequence star appears utterly stable. It shines with constant luminosity, constant color, constant temperature. This stability is the hallmark of hydrostatic equilibrium, the balance between gravity and pressure that fusion makes possible. The newly born star, having just reached the main sequence, will spend the next hundreds of millions or billions of years in this stable state. It has completed its formation. The gravitational collapse has ended. The accretion has ceased. The disk around it may persist for a while longer, perhaps long enough for planets to form, but eventually it too will dissipate, blown away by stellar winds and radiation pressure, or incorporated into planets and smaller bodies. The star itself, however, will endure. It will shine steadily, converting hydrogen into helium in its core, slowly evolving but fundamentally stable. It has become part of the stellar population of the galaxy, one more point of light among hundreds of billions. From a dark, cold molecular cloud, from a collapsing core, from a protostar hidden in dust, a true star has emerged. And in that emergence, in that transformation from darkness to light, from cold to heat, from potential to actuality, we see one of the universe's most profound processes. Star formation is how the cosmos builds complexity, how the simple hydrogen and helium left over from the Big Bang are forged into heavier elements, how energy is generated and distributed, how the raw materials for planets and life itself are created and dispersed. Every star we see in the night sky has undergone this journey. Our own sun was born in this way, some 4.5 billion years ago, in a molecular cloud long since dispersed. The calcium in our bones, the iron in our blood, the carbon in our DNA, all were created in stars that formed, lived, and died before our sun was born, their ashes incorporated into the molecular cloud that gave birth to our solar system. The planetary legacy, worlds in formation. The story of star birth does not end with the star itself. Around the newly formed star, orbiting in the equatorial plane, lies a disk of gas and dust. This protoplanetary disk is the remnant of the angular momentum of the original collapsing cloud, the matter that couldn't fall directly onto the star due to its rotational motion. This disk is the birthplace of planets. The disk is not merely a featureless expanse of material. It has structure, complexity, gradients in temperature and density. Near the star, where temperatures can exceed 1,000 degrees, only the most refractory materials can remain as solids. Silicates, metals, these can withstand the heat. Farther out, beyond a certain distance, often called the snow line or frost line, temperatures drop low enough for water to condense as ice. Beyond this line, at perhaps 3 to 5 astronomical units for a sun-like star, the solid material available for planet building dramatically increases as water ice adds to the rocky material. Still farther out, other volatiles condense. Methane, ammonia, carbon dioxide, all can form ices in the cold outer regions of the disk. This radial variation in composition will determine the types of planets that form at different distances from the star. Rocky planets will form in the hot inner regions. Icy and giant planets will form beyond the snow line, where more solid material is available. The process of planet formation begins with dust. The disk contains dust grains, tiny particles of rock, metal, and ice, each perhaps a micrometer or so in size, about the width of a bacterial cell. These grains collide with each other as they orbit the star. Sometimes, if the collision is gentle enough and if the grains have the right surface properties, they stick together. Electrostatic forces and molecular bonds can cause grains to adhere. Over time, grains grow. 2 grains become one slightly larger grain. This larger grain collides with others, growing further. The process is slow and fraught with difficulties. Grains that grow beyond a certain size tend to bounce off each other rather than sticking. Larger grains also drift inward through the gas disk faster than they grow, potentially falling into the star before they can become large enough to be gravitationally bound. Yet somehow, in many disks, grain growth succeeds. The dust grains gradually settle toward the midplane of the disk, forming a thin layer of solid material embedded in the gas. This layer becomes denser than the surrounding gas, potentially reaching densities where gravitational instabilities can occur. Clumps within the dust layer can collapse under their own gravity, rapidly forming larger bodies. Through some combination of these processes, sticking and gravitational collapse, grains eventually grow to kilometer-sized bodies called planetesimals. Once objects reach this size, a new phase of growth begins. Planetesimals have enough gravity to attract nearby material. They can grow through a process called accretion, sweeping up smaller bodies in their vicinity. In the inner solar system, where our own rocky planets formed, planetesimal growth leads to the formation of planetary embryos, objects perhaps the size of the Moon or Mars. These embryos continue to grow through collisions with other embryos and with remaining planetesimals. The process is violent. Giant impacts, collisions between Mars-sized bodies, shape the final architecture of the inner solar system. The Moon, in fact, is thought to have formed from the debris of such a giant impact between the young Earth and another planetary embryo. In the outer solar system, beyond the snow line, more solid material is available because of the condensation of ices. Planetary embryos can grow larger more quickly. If an embryo grows massive enough, perhaps reaching 10 to 20 times the mass of Earth, its gravity becomes strong enough to attract and hold onto the gas from the surrounding disk. This runaway accretion of gas is how giant planets form. Jupiter and Saturn are primarily composed of hydrogen and helium gas, but each has a core of rock and ice at its center. These cores formed first, over a few million years, by the accretion of planetesimals and embryos. Once the cores reached critical mass, they began to gravitationally attract gas from the disk. The gas fell onto the growing planet, forming a thick envelope. This accretion continued until the disk dissipated, either because the central star blew the gas away with its winds and radiation, or because the gas was used up in forming planets. The timing is crucial. If the disk dissipates before a planetary core reaches the critical mass needed to accrete gas, the result is an ice giant like Uranus or Neptune rather than a gas giant like Jupiter or Saturn. Uranus and Neptune have substantial rock and ice cores but only relatively thin envelopes of hydrogen and helium. They likely formed later or farther out, missing the window when gas was still abundant. Observations with powerful telescopes like the Atacama Large Millimeter Array have revealed the structure of protoplanetary disks in exquisite detail. Many disks show rings and gaps, dark bands where the density of dust is reduced. Some of these gaps are likely carved by newly formed planets. As a planet orbits within the disk, its gravity creates a disturbance, clearing a gap in the disk along its orbital path. The existence of these gaps in young disks suggests that planet formation can begin very early, perhaps within the first million years of a star's life. Other disks show spiral arms, similar to those in spiral galaxies but on a much smaller scale. These spirals can be driven by gravitational instabilities in the disk or by the gravitational influence of a massive planet or companion star. The spiral waves can concentrate material, potentially triggering planet formation or influencing the migration of already formed planets. Planet migration is an important process in many planetary systems. Planets don't necessarily stay in the orbits where they formed. Gravitational interactions with the disk can cause planets to migrate inward or outward. A planet orbiting within a gas disk experiences gravitational torques from the disk material. Depending on the detailed structure of the disk, these torques can cause the planet to spiral inward toward the star or drift outward. Many of the exoplanets discovered around other stars are hot Jupiters, giant planets orbiting very close to their parent stars, completing an orbit in just a few days. These planets almost certainly did not form where we find them. Temperatures so close to the star would have been far too high for ices to condense, and without ices, there wouldn't have been enough solid material to build a giant planet core. Instead, these hot Jupiters likely formed farther out and then migrated inward through the disk, settling into their current close-in orbits. Our own solar system may have undergone significant migration as well. There are models suggesting that Jupiter and Saturn underwent a complex dance of migration, moving inward and then outward, driven by interactions with a disk of planetesimals. This migration could have scattered the outer solar system, sending many planetesimals into the inner solar system where they bombarded the newly formed terrestrial planets. The diversity of planetary systems we've discovered around other stars is astounding. Some stars have super-Earths, planets larger than Earth but smaller than Neptune, orbiting at distances where Earth orbits our Sun. Our solar system has no such planets. Other systems have multiple giant planets in complex orbital configurations. Some have planets on highly eccentric orbits, swooping in close to the star and then swinging far out. Some have planets orbiting backward, in the opposite direction to their star's rotation. This diversity reflects the complexity of the planet formation process. Slight differences in the initial conditions of the disk, in the timing of planet formation, in the masses of the planets that form, can lead to radically different final outcomes. There is no single template for planetary systems. Each star's planets are shaped by a unique history of formation, migration, and dynamical evolution. The disk around a newly formed star typically persists for a few million years, perhaps up to 10 million years. During this time, the gas is gradually dispersed by photoevaporation, driven by ultraviolet radiation from the central star, and by accretion onto the star and onto forming planets. Observations show that most stars older than 10 million years no longer have detectable gas disks. The gas is gone, blown away into space. dust can persist longer. Some stars retain dusty debris disks for hundreds of millions of years. These debris disks are thought to be maintained by collisions among asteroids and comets in the system, grinding them down into dust which then slowly spirals into the star or is blown away by radiation pressure. Our own solar system has such a debris disk, a faint cloud of dust produced by asteroid collisions and cometary outgassing, though it is far too faint to be detected from another star system. By the time the disk has fully dispersed, the architecture of the planetary system is largely set. The planets have formed, their orbits have stabilized, and the system settles into a configuration that may persist for billions of years. Small bodies, asteroids, and comets continue to orbit in belts and scattered populations, occasionally perturbed into planet-crossing orbits where they may collide with planets, delivering water and organic materials or creating craters. The formation of planetary systems is one of the most active areas of research in astronomy. New discoveries come regularly, challenging our understanding and forcing us to refine our models. We are living in an extraordinary era when, for the first time in human history, we can observe planetary systems in formation, see disks around other stars, detect young planets in their natal environments, and test our theories against a diverse population of exoplanetary systems. The eternal cycle. And so, from the cold darkness of a molecular cloud, a star is born. Over millions of years, gravity's patient pull transforms diffuse gas into a blazing sphere of plasma, fusing hydrogen in its core, shining by the light of nuclear fire. Around it, a disk of dust and gas gives birth to planets, to worlds that will orbit their star for billions of years. This process has been repeated countless times throughout the history of the universe. Every star we see began this way. Every planetary system emerged from a protoplanetary disk. The pattern is universal, the outcome varied. Each star is unique, each planetary system distinct, yet all share this common origin. The cycle doesn't end with a star's birth. Stars live, evolve, and eventually die. Low-mass stars like our Sun will expand into red giants, gently shedding their outer layers to form planetary nebulae, leaving behind dense white dwarf cores that cool slowly over trillions of years. Massive stars will explode as supernovae, scattering the elements forged in their cores and in the explosion itself across space, enriching the interstellar medium with heavy elements. These heavy elements, created in stars and dispersed by stellar winds and supernovae, mix into new molecular clouds. When the next generation of stars forms, they are born from material that has been enriched, that contains not just hydrogen and helium but carbon, oxygen, silicon, iron, all the elements of the periodic table. This recycling of material, this cosmic alchemy, is how the universe builds complexity over time. Our own bodies are made of stardust, quite literally. The atoms in our cells, except for the hydrogen, were created in stars that lived and died before our sun was born. We are the universe made conscious, matter contemplating itself, the end product of billions of years of cosmic evolution, of stellar births and deaths, of the slow assembly of complexity from simplicity. As you drift towards sleep tonight, reflect on this connection. You are part of an unbroken chain that stretches back through the formation of Earth, through the birth of the Sun, through the clouds of gas and dust from which the solar system formed, through previous generations of stars, back to the first stars that formed when the universe was young, and ultimately to the Big Bang itself. You are made of the same stuff as the stars, governed by the same physical laws, participating in the same grand cosmic dance. The atoms in your hand were forged in the hearts of ancient suns. The energy you used to breathe today, to think, to live, came originally from fusion reactions in the sun's core, 8 light minutes away. In the grand scope of cosmic time, in the vast expanse of space, human existence is brief and small. But it is also profound. We are the way the universe knows itself. In us, in our consciousness, the cosmos has developed the ability to wonder at its own existence, to ask questions about its origin and fate, to find beauty in the night sky, to trace the journey from molecular cloud to star to planet to life. Let this perspective bring you peace. Your worries, your stresses are real and valid on the human scale, but they are also temporary, fleeting against the backdrop of deep time. The processes that created the stars are still at work. Stars are being born right now, at this very moment, in molecular clouds scattered throughout the galaxy. The cycle continues, patient, inexorable, beautiful. Relax into this knowledge. Let the vast scales of time and space wash over you. Let them put your daily concerns in perspective. You are part of something immense, something ancient, something ongoing. The story of the universe is your story too. As you close your eyes and drift towards sleep, imagine yourself back in that molecular cloud, floating peacefully in the cosmic darkness, witnessing the slow ballet of star formation. Feel the timescales stretch out. Feel yourself becoming part of the eternal rhythm of collapse and ignition, of darkness giving way to light, of potential becoming reality. Sleep well, knowing that you are stardust contemplating stars. Rest in the knowledge that the processes that created you are as natural as the birth of stars, as inevitable as gravity's pull, as beautiful as the light emerging from darkness. And if you've enjoyed this journey through the cosmos, if these thoughts have brought you peace or sparked your wonder, consider subscribing to our channel, Deep Science Sleep. We explore the universe together, one sleepy science story at a time, finding rest and perspective in the grand narratives of nature. Good night, star traveler. Sleep well.